In this video, I just need to explain what relative density means. Now, the word relative kind of means to relate to something. Now, in this case, relative density means I'm relating the density of a substance to the density of water. Maybe let me use some illustration to paint the picture of what I mean by relative density or relative something. Right before me here, I'm having 3 sticks. They're just sticks I've wrapped with paper. So there is this stick, there is this one, and then there is that one. I am a kindergarten mathematics teacher, and I need these sticks of this height so that I use them to help me in counting as I'm teaching addition to kindergarten kids. So now what happens is that I send out some kids to go to the forest or to the bushes to just go and cut down some of these sticks, like of this size. So of course, as these kids go to cut down these sticks, they come back with various sizes of sticks. This is my standard height. This is the height of the stick that I want. But however, as these kids go out to cut the sticks, some of them come back with sticks that are shorter than my standard height or the standard height that I want, and some are coming back with sticks that are longer than the standard height that I want. Maybe I can't exactly I can't afford to have all the sticks of the standard size that I want. So I decide to make a compromise and I say, okay, I'll tolerate some sticks that are probably that are not very far away from the standard size that I want. So if I want to determine the sticks that are not very far away from the size that I want, the standard size that I want, then it means I'm going to start carrying out I may carry out what we call the relative height of the sticks. Now, by relative height, I mean that I am going to get my standard stick size, which is this one, and I am going to compare the height of this stick with the height of all these other sticks that they've brought. That is what we are calling relative height. So in this case, the relative height is going to be it's going to be a ratio, or it's going to be an index, or it's going to be a number that is going to show me how high the other sticks are in relation to my standard height. So I'll call that relative height. So let me just do an illustration on just these 3 sticks. So now we are having these 3 sticks. We have stick A, stick B, and stick C. And I am saying that stick B is going to be more of like my standard. I sent these kids out into the bush, and I expect that they get me sticks of this height specifically. But in the process, they got me sticks that are shorter, and some got me sticks that are longer than my standard height. So let's assume my standard height is 10 centimeters. So the standard height of the stick that I want is 10 centimeters long. So meaning that if one of the kids gets me a stick that is taller than this one, then I can go ahead and find how long is this stick in relation to my standard height. If somebody went and got me a stick that was shorter, I would go and say, how long is this stick in relation to my standard height? So what do I do? So I'll go ahead and find the relative height of stick C. So it means that the relative height of stick C is going to be equal to, what I'm going to do is that I'm going to measure the height of this stick C. Let's say the height of this stick C is 20 centimeters. So it's going to be the height of stick C divided that by the height of my standard stick, which I'm calling stick B. And in this case, the height of stick C is 20 centimeters with this long one, stick C. Divide that by the height of the standard height, which is 10. And I'm going to get this is also in centimeters. Of course, the units will cancel out. 20, this gives us 2. And so it means that my relative height, the relative height of stick C is 2. Let's look at the relative height of stick A. So the relative height of stick A is going to be the height of stick A divided that by the height of the standard height, which is B. The height of stick A in this case, let's assume this is 5 centimeters. It's halfway, this one. It's an assumption. So this is 5 centimeters, divide that by 10 centimeters, and we shall end up with a half. So now why am I making these calculations of relative height? I'm trying to explain the significance of what we mean by relative height. Like I said, this is my standard height, B. This is the height I want. It's the height I've chosen. It is my standard height, B. But then now, some sticks are taller. So in finding the relative height of stick C, we divide the height of C, divide that by the height of the standard, the base height. And we got 2. But when we did this, when the thing was shorter, for all the stick that was shorter than my standard, the height of A, divide that by the height of stick B, I got a half. Now, the question is, what do these figures mean? This is what they mean. It means that relative height, if the relative height of stick C is 2, it means that this stick is 2 times taller than my standard height. That is what it means. Likewise, this half, which is relative height, a half, this a half means that this means that this stick is halfway the height of my standard height, B. They're just ratios that help us to know the magnitude of something in relation to something. For example, when I just look at 2, I know that this stick C is 2 times taller than this one. Let's say I got some other stick, and let's say I got its relative height to be, let's say, 6. It would mean that that very stick is 6 times taller than the standard height that I want. That is why we are dividing this by the standard height. We are dividing this by the standard height B. Why? Because this height is what I wanted. So that is the concept of relative height. Now I want us to relate this to what we mean by relative density. It is going to be exactly the same thing here. Like in my earlier illustration where I was using sticks, the same reasoning I used there is the same reasoning that is at play here. That relative density is simply the ratio of the density of a substance over the density of water. So in this case, the density of water is our standard. I know that the relative height of this stick is 2. This means that this stick is 2 times the height of my standard height. So it means that if I just only know that if I just know the relative height of this stick, and I know the height of my original, let's say this is 10 centimeters, so meaning that if I want to find the real height of this stick and I know its relative height, I'm simply going to say it is 2 times the height of the standard, and I'm able to get the height of this thing. Likewise, the relative height of this is a half, right? So it means that if I want the height of A, and I know its relative height to be a half, it means that it is a half of the standard height that I had chosen, the standard stick. So if I need to find the height of this, I simply going to get a half, multiply that a half by the standard height, and I'll be able to get the height of this stick. So that is going to play out exactly the same even when we're dealing with relative density of substances. Let's say I have the relative density of a certain liquid to be like, it's 3. That's relative density of a certain liquid X, it's 3. If I want to find the density of that very liquid, I know it's simply going to be 3 times the density of water. Now we all know that the density of water is 1,000 kilograms per meter cubed. So it's going to be 3 times the density of water, and I'll be able to get the density of that liquid X. So when it comes to relative density, by definition, relative density is simply given as the ratio of the density of the substance to the density of water. That is in general terms. However, the formula for relative density can be represented in many other ways. So, like we said, relative density is density of substance over density of water. Density is equal to mass over volume, so it is mass of the substance over volume of substance. Divide that by the mass of water over volume of water. Of course, because we are dividing these two, the reciprocal of this is a volume of the water over mass of substance. Multiply that by mass of substance over mass of water, and definitely this volume of water and volume of substance, they will cancel out. it means that the volume of this substance and the volume of the water are the same for them to be able to cancel out. And when they cancel out, you remain with relative density being equal to mass of substance over mass of water. So what does that mean? This gives us another formula for relative density. So relative density can also be defined as the ratio of mass of a substance to the ratio of mass of an equal volume of water. It is important that it is an equal volume of water because these volumes cancel out because they are equal. Otherwise, if these volumes are not equal, then this would not hold. That is why the other way we can look at relative density is the ratio of mass of a substance to the mass of an equal volume of water. Now we also know that mass is directly proportional to weight. I mean, we all know that weight is given by mass times gravity. Gravity is a constant term. So it means that weight and mass are directly proportional. The higher the mass, the higher the weight. The lower the mass, the lower the weight. So much as we are saying that relative density can be given as the ratio of mass of a substance divided by the mass of an equal volume of water, it means that in the place of mass we can also say relative density can be given as also the ratio of weight of a substance to the weight of an equal volume of water. Now, so far we have looked at 3 ways we can express relative density. Relative density can be expressed as the ratio of density of a substance to the density of water, the ratio of mass of a substance to mass of an equal volume of water, the ratio of weight of a substance to weight of an equal volume of water. That is in general terms. Now let's look at other ways of finding relative density. Let's look at how we can find relative density in solids. Now when it comes to solids, the relative density can also be given as mass of a substance in air divided by the apparent loss of mass in water. Now, what is this apparent loss of mass in water? Now, of course, when you are in water, you experience a certain force that acts on you. I'll use this simple illustration, but we shall explain this further when we are looking at Archimedes' principle. This right here is probably a spring balance, and this is a support of this spring balance, and this is a solid. This is a solid in air, and definitely when it is in air, we will be able to read off its weight. Now, when it comes to this, we can still bring this solid and put it in water and still read the spring balance. Now you realize that when the spring was in air, when this solid was in air, let's say it weighed, let's say 10 newtons, according to the spring balance. But then I got this very spring balance and dipped this solid in water, and when I dip it in water and then I read my spring balance again, I find that the spring balance here is, let's say, 9 newtons. Now, the question is that why is it that when it is in air, it is 10 newtons, and then when I come and bring the same solid and immerse it in water with the same spring balance, it's going to measure less than it did here? This is because when this thing is immersed in water, it is experiencing a certain force acting from downwards. This force that it is experiencing from downwards is going to cause it's going to cause the spring balance to record a lesser weight. In other words, this block or this solid loses some weight as it drops in water, and now that weight is lost because of a certain force that is within water, and that is the upthrust force. Of course, when this solid is in liquid, it's going to experience forces on all sides, but the downward force is the one that is the strongest, and it is the one that causes this drop in. This drop in the weight is what we are calling the apparent loss of the weight of this solid. That apparent loss, we get it by is gotten by, we get the weight of that solid in air, subtract the weight of that solid when it is in the liquid. When you subtract those two, the weight in solid in air and the weight in solid in liquid, we get the apparent loss of weight of that solid. Now that apparent loss of weight of that solid is because of the upthrust. We shall discuss more about this upthrust force when you are dealing with Archimedes' principle. So now this apparent loss in weight is what we are talking about in this denominator here. That the relative density for solids, we can get it first by determining the mass of the substance in air, which is what we are doing here, dividing that by the apparent loss of the mass when the thing is in water. And that's how we can get. So since mass and weight are directly proportional, it's the same story here. We can look at it as mass or weight. We can say mass, weight of a substance in air, divide that by the apparent loss in weight of that solid substance in water. And like I have been explaining, that apparent loss in weight or mass is given by the weight in air, or call it the mass in air, subtract weight in water, or call it the mass in water. That's the apparent loss. That is how we can find relative density in solids. We can also find relative density in liquids using a similar technique. We can find the relative density of a liquid by finding the ratio of the apparent loss in mass of the substance when in the liquid to the apparent loss in mass of the substance when in water. Like I had earlier said, there is such a thing as apparent loss in weight of a substance or of a solid. Now, here we are trying to find the relative density in liquids. If I want to find the relative density of this liquid, for example, remember the water is more of our standard. We are trying to find the relative density. In other words, we are trying to find the density of this liquid with respect to the density of water. So, besides just getting the density of the liquid and dividing that by the density of water, we can also use this formula. It means that we're going to find the apparent loss, and by these are the procedures. This is how we go about it. It means that we're going to get a spring balance, measure this object or this solid in air, and then we record its weight in air. After recording its weight in air, we go get this thing and drop it in there, in this liquid X. Now, because of this upthrust force that I had spoken of earlier, there's going to be a reduction in the weight, a drop in the weight of this liquid while it is immersed in this liquid. And so it means that we are going to register a weight while this thing is in the liquid. Then we are going to get this same solid as well and drop it in water, and we are going to register another weight, another reading there, and we shall call it our weight when this solid is immersed in water. And of course, remember, because of the upthrust force in these containers, the weight in air is always going to be greater than the weight when this thing is immersed in this liquid, and it's also the weight in air is always going to be greater than the weight of this same solid when it is immersed in water. So what does that mean? It means that there is an apparent loss when this thing was dropped in liquid, and there's also going to be an apparent loss in weight when this solid was dropped in that water. So what does that mean? It means that if we find the ratio of this apparent loss, or we get the apparent loss in the liquid, divide that by the apparent loss in the water, we will be able to get the relative density of this liquid. So it means that the relative density here is going to be the apparent loss, which is given by the weight when the thing was in air minus the weight when it was dipped in the liquid. Divide that by the weight when the thing was in air minus the weight when it was immersed in water. So this expression is exactly what is explained here, that for liquids the relative density can be found out by finding the apparent loss in mass of a substance when in the liquid. The liquid can be anything. Divide that by the apparent loss in mass of a substance when it is in water. Like we said, mass and weight are directly proportional. So what does that mean? It means that it can still be apparent loss in weight of a substance when in liquid. Divide that by the apparent loss in weight of a substance when in water. And like I have been illustrating, this is what I mean: mass of the substance in air, or mass of the solid in air minus mass of that solid in the liquid. Divide that by mass of the substance in air minus mass of that substance when in water. It's the same way the mass can be substituted by weight. Weight of the substance in air minus weight in the liquid, divide that by weight of air minus weight in water. This is the apparent loss in weight in the liquid, this is the apparent loss in weight in water. And definitely this is the same as saying the upthrust experienced when the thing is in the liquid, divide that by the upthrust experienced when the solid is in water. This ratio enables us to get the relative density of the substance. We have quite a long question here. I guess we will have to first summarize it. It says that a block of mass 0.1 kilograms is suspended from a spring balance when the block is immersed in the water of density 1000 kilograms per meter cubed. The spring balance reads 0.63 newtons. When the block is immersed in a liquid of unknown density, the spring balance reads 0.7 newtons. The question is, find the density of the block and the density of the liquid. So we'll go ahead and first summarize this question. So we're talking about a block. It is having a mass of 0.1 kilograms. So meaning mass of the block is going to be 0.1 kilograms. And it is suspended from a spring when the block is immersed in water of density that. So meaning that the density of the water is 1000 kilograms per meter cubed. Now it continues to say, when the block is immersed in water of density 1000 kilograms, the spring balance reads 0.63 newtons. So when the weight in water, when this is the weight, when this solid or the block is immersed in water, it's going to weigh 0.63 newtons. Full stop. We continue and say, when the block is immersed in a liquid of unknown density, so meaning that when it is in its weight in a liquid whose density is not known, so meaning that the density of the liquid is not known, the weight of the liquid, the question says the spring balance reads 0.7 newtons, so it's going to read 0.7 newtons. Find the density of the block. So we need the density of the block. So the density of the block is also unknown, and then the density of the liquid, you also do not know the density of the liquid. From what the question has given us, you can see that we are having, this is mass of the block. We have weight of when that block is immersed in water. We have the weight of that block when it's immersed in the liquid. And we have the density of the liquid, but of density of water, we do not know the density of the liquid, and we also do not know the density of the block. We need to find these two out. So what we do here is simple. First of all, let's find the weight of the block. We know that the mass of the block is 0.1 kilograms. So the weight of the block, or call it the weight of the block in air, is going to be 0.1, which is the mass of the block given here. Multiply that by the acceleration due to gravity, which is 9.81. And so the weight of the block is going to become 0.981 newtons. We have the weight of the block. We have the weight when the block is immersed in water. We have the weight of the block when it's immersed in the liquid whose density we do not know. So let's go ahead and find the relative density of the block. So the relative density of the block is going to be given by, from our previous session, we said that the relative density is given by weight of a substance in air divided by the apparent loss of weight in water, and that is exactly what we are going to do here. So from here we know that relative density of the block, relative density of the block, let me do it like that, is going to be giving us the weight of the block in air, divide that by the apparent loss of weight. Now the apparent loss of weight in water means it's going to be the weight of the block minus the weight of that block when it is in water. So this is going to become the weight of the block. We got it as 0.981. Divide that by the apparent loss in weight, which is going to be the weight of the block, which is 0.981, minus its weight in water, which is given by 0.63. And of course, when we divide those two, we end up with the relative density of the block as... Now that we found the relative density of the block, we can go ahead and find the density of the block as the question requires us. We say that if we know the relative density of something, we just simply have to multiply this by the density of water, because remember this relative density 2.7949, this means that this block is 2.7 times more dense than water. So if we want to find the real density of this block, we simply get the 2.7949 and multiply that by the density of water, which is 1000. Or maybe let's get that from a formula we quoted earlier. Still, in our previous session, we said that relative density is the density of a substance over density of water. So I'll quote that again. Relative density is given by density of a substance divided by density of water. Now we have the relative density of this block, which in this case is given by 2.7949. So it's going to be 2.7949 is going to be giving us the density of the substance. Now, of course, the density of the substance, as far as this question is concerned, it's the density of the block which we are looking for. Divide that by the density of water, which is given by 1000 kilograms per meter cubed. So this is going to be, we make the density of the substance, the subject of the formula becomes this times that. So it's 2.7949, multiply that by 1000 kilograms per meters cubed, and that is going to give us 2794.9, and that is kilograms per meter cubed. So this is going to be the density of the block. Now that answers Roman 1 of our question. Part 1 of our question is answered. Now we go ahead and answer part 2. We need to find the density of the liquid, and again, for us to find the density of the liquid, first, as far as the way this question is structured, we are going to first find the relative density of that liquid. After getting the relative density of that liquid, then we are going to multiply that relative density by the density of water, like the way we've done here, and we will be able to get the density of the liquid. From our previous session, this is the formula we quoted. Apparent loss of mass. In this case, since the question says weight, we are going to say apparent loss in weight of the substance when in liquid, divide that by the apparent loss in weight of the substance when it is in water. So what is that apparent loss? How is it given? So relative density is apparent loss of weight. So meaning we are going to get the weight of the block minus the weight of that block when it is in the liquid, divide that by the weight of the block minus the weight of that block when it is in water. So this is the apparent loss of weight of the block when it is in liquid, divide that by the apparent loss of the weight when it is in water. So we go ahead and calculate. The apparent loss of weight when the thing is in it's going to be 0.981 minus its weight when it is in the liquid. In this case, it's 0.7 newtons. Divide that by 0.981 minus its weight when it is in water. The weight of the solid in water is 0.63. And by the way, this apparent loss in weight is same as saying the upthrust experienced when it is in the liquid, divide that by the upthrust experienced when it is in water. So to continue, this is going to become 0.981 minus 0.7 is going to give us 0.281, divide that by 0.351. That's the relative density. Now that we have the relative density, we can go ahead, of course, after finding the relative density, we can go ahead and find the density of the liquid like the question requires. We know that relative density is given by density of a substance divided by density of water. Now the substance, in this case here, we're dealing with the liquid, so it's going to be the density of the liquid. So we make density of the liquid the subject of the formula. Is going to give us the relative density, multiply that by the density of water. Now in this case, it's going to be the relative density of the liquid. We got it here as this over that, so it is 0.281, divide that by 0.351, multiply that by the density of water, which is 1000 kilograms per meter cubed, and when we find that, our answer is going to be 800 kilograms per meter cubed, and that is the density of the liquid. The other example here is this. A solid of mass 0.2 kilograms is suspended from a spring balance when the block is immersed in water. The spring balance reads 0.84 newtons. When the block is immersed in a liquid of known density, the The spring balance reads 0.95 newtons. The question requires us to find the density of the block and then the density of the liquid. So we'll begin off by summarizing our question. The solid has a mass of 0.2 kilograms. So meaning that the mass of the solid is 0.2 kilograms. So 0.2 kilograms, let's find the weight of this liquid already, of the solid. So meaning that the weight of this solid is going to be equal to 0.2 kilograms. Multiply that by the acceleration due to gravity, which is 9.81, and that gives us 1.962 newtons right there. So that's the weight of the solid, or call it the weight of the solid when it's in air. So we continue. When the block is immersed in water, the spring balance reads 0.84 newtons. So meaning when this solid, or let's call it a block. So when this block is immersed in water, so the weight of this block when it is immersed in water, the question says the weight is 0.84 newtons. Now when the block is immersed in a liquid whose density is known, the spring balance reads 0.95. So when the weight of this block when it's immersed in a liquid whose density we know, the weight is 0.95 newtons. So they ask us to find the density of the block, so we are required to find the density of the block, and we also need to find the density of the liquid. So we need to find the density of the block and the density of the liquid. So to find the density of the block, we are going to use this approach. We have the weight of the block in air, we have the weight of the block when it's in the liquid, we have the weight of the block when it's in water. So meaning by the density of the block, we can find the relative density of the block. After finding the relative density of the block, we multiply that by the density of water and we're able to get the density of the block. And it's the same approach we are going to use for the density of the liquid. We are going to first find the relative density of the liquid. After getting the relative density of the liquid, we multiply that relative density of the liquid by the density of water, and we're able to find the density of the liquid. So let's get started with the working. First of all, to get the density of the block, to find the density of the block, we are first going to find the relative density of the block. The relative density of the block is given by the weight of the block when it is in air, or we'll call it the weight of the block when it's in air, divide that by the apparent loss of the weight of the block when it is immersed in water. So that means it's going to be the weight of the block minus the weight of the block in water. So it means that it's going to be the weight of the block. In this case, it's going to be 1.96. Divide that by the weight of the block minus the weight when it's in water, which is 0.84. And this definitely is going to give us 1.749. Now that we have the relative density of the block, we can go ahead and find the density of the block itself. We know that relative density is also given by density of the block over density of water. Since we want the density of the block, we make density of the block the subject of the formula is going to be equal to the relative density of the block, multiply that by the density of the water. In this case, the relative density of the block, we got it up there as 1.749, multiply that by the density of water, which is 1,000 kilograms, and that is going to give us 1749, that is in kilograms per meter cubed, and that is our density of the block. So in the same way, we are going to find the density of the liquid, and by finding the density of the liquid, we are going to first find the relative density of the liquid. Now to find the relative density of the liquid, we know that relative density of the liquid is going to give us the apparent loss of weight of this block when the thing was in the liquid, divide that by the apparent loss of weight when it's in water, or call it the upthrust experienced by the block when it's in the liquid, divide that by the upthrust experienced by the block when it's in water. This is the same as saying the apparent loss of weight, that is going to be the weight of the liquid when it is in the weight, this is given This upthrust experienced by the block when it's in the liquid is given by the weight of the block, or when the weight of the block in air, minus the weight of the block when it is in that liquid. Divide that by the weight of the block when it's in air, minus the weight of the block when it is in water. This is going to be equal to, the weight of the block in air is 1.962, subtract the weight when it's in the liquid, 0.95. Divide that by the weight of the block, 1962. Divide that by its weight when it's in water, which is 0.84 newtons. And of course, when you divide that, the ratio, you get 0.902. This is the relative density of the liquid. So now that we have the relative density of the liquid, we multiply that by the density of water. But for the sake of showing working, we shall say that again, relative density is still the ratio of the density of the liquid, divide that by the density of water. We're interested in the density of the liquid, so it means that we make this the subject of the formula. The density of the liquid is given by relative density of the liquid, multiply that by the density of water. This is going to give us relative density of the liquid, which is 0.902. Multiply that by the density of water, which is 1000. And definitely this is going to give us 902 kilograms per meter cubed. In this session, I'm going to describe an experiment that we can use to determine the density of an irregular solid which floats in water. Now, the overall mind behind this experiment is simply this. We are going to first get the relative density of the object, and then after getting the relative density of the object, we are going to go ahead and multiply it by the density of water. When we get the relative density of the object, multiply that by the density of water, we will be able to get the density of that irregular object that we are talking about, just like the way we've been doing in our previous sessions in the calculations. So right before us we are having, this is called a spring balance, and we have definitely tied something on it. This is the solid that floats in water, the irregular solid that floats in water, whose density we want. So as we go ahead to find the density, first of all we are going to put a thread. We are going to tie a thread to this solid and get the weight of this irregular solid in air, and we are going to call that W1. That's our first step. Since this solid floats, we need it to first get fully immersed in water. So it means we are going to tie a sinker to this solid so that it sinks inside. Now that we have attached a sinker to this solid, now before we actually put this into water, we need to first get the weight of these two. So what we do is that we get the weight of the solid and the sinker, and we call that W2. We get them when they are still outside, before we sink them in water. We take the reading on the spring balance and we determine the weight of the solid and the sinker. After determining the weight of the solid and the sinker, we now immerse both of them in water. And when we immerse both of them in water, of course there is upthrust that is going to act on them, so meaning there's going to be a drop in the reading here. So we are able to determine the weight of the stone and the sinker when they are both immersed in water, and we call that W3. Then afterwards we are going to take away the irregular solid that sinks in, that floats on water. Then we get the weight of the sinker alone when it is immersed in water, and there we are able to record that, and we call that our weight W4. In our previous sessions, remember we said that the relative density of a solid can be given by the weight of the substance when it is in air, divide that by the apparent loss of weight in water. So in this experiment, this is what we are trying to arrive at. This solid that we are dealing with, first of all, does not sink in water. So because it does not sink in water, that's why we use the sinker, so that it enables that thing that floats on water, that irregular solid, to sink in water. So now that it is able to sink in water, our objective here is simple: to get its weight when it is in air, and which we already got, and then the apparent loss in weight of water. This write-up is coming from that premise. that the relative density is going to be W1. W1 is the weight of the solid when it is in air. Divide that by the apparent loss in weight, and the apparent loss in weight is given by the weight when it is in air minus the weight when it is the regular solid is in water. Now, this solid whose relative density we're looking for, when it was in water, it was there together with the sinker. That is why the weight that was recorded here was the total weight of the solid and the sinker. But now for us, we are only interested in the weight of the solid. So what does that mean? It means that we are going for us to get the weight of the solid in air minus the weight of that irregular solid in water, means that the weight of that irregular solid in water is, we're supposed to first get the weight of this combination, which is W3, the weight of the solid and the sinker when they're in water, minus the weight when the sinker is in water alone, which is W4. That is the essence of this W3 minus this W4. This W3 minus W4 is, we are trying to get the total weight of these two minus the weight of the sinker, so that we're able to get the weight of the solid when it is immersed in liquid. And the weight when it is immersed in weight in air minus weight when that solid is immersed in the liquid gives us the apparent loss in weight of the solid. And definitely this is how we get the relative density. After getting the relative density of that solid, then we can go ahead and find the density of the irregular solid by getting the relative density we've gotten in our previous step, multiply that by the density of water. And that is definitely how we find, or that is the description of the experiment to determine the density of an irregular solid which floats in water. In this session, we are going to describe an experiment to determine the relative density of a liquid. Now, from our previous sessions, we said that to find the relative density for liquids, we need to find the apparent loss in mass or the apparent loss in weight of that substance, of a solid when it is immersed in that liquid whose density we want. Divide that by the apparent loss in mass or the apparent loss in weight of a substance, in this case a solid, when that solid is immersed in water. Now we need to define this, verify this experimentally. So to verify this experimentally, we're definitely going to get our weight of the solid when it is in air. This is our spring balance and this is the solid or the substance. So we're going to get our weight of this solid when it is in air. Then we transfer that solid and we completely immerse it in water. And we take the reading on the spring balance, and that becomes our WW, which is the weight of the solid in water. After getting our weight of solid in water, then we take it away from water and we immerse it in a liquid whose density we want. We completely immerse the solid in the liquid whose density we want. We take readings from the spring balance and we record the weight of the solid when it is completely immersed in the liquid. Upon doing that, we're able to find the relative density by finding the apparent loss of weight of the solid when it was immersed in the liquid, which is weight of the air minus weight of the liquid. Divide that by the apparent loss in weight of the solid when it is immersed in water, which is the weight of the solid when it is in air minus the weight of the solid when it is in water. That is how we find relative density of a liquid experimentally. This apparent loss can still be referred to as the upthrust in the liquid. Divide that by the upthrust experienced by the body or by the solid in water. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.